The danger does not announce itself with color or movement. It hides in texture. The rainforest canopy filters sunlight into fragments that slide across leaves, bark, and hanging vines, revealing a world that appears calm, even gentle. Caterpillars cling motionless to branches and trunks, their bodies softened by camouflage, greens that mimic moss, browns that echo bark, tufts that resemble lichen or fungal growth. They look inert, harmless, almost decorative. The trap begins precisely there, in the assumption that softness equals safety. You never see the spines. You feel something else first. A faint itch on the forearm where fabric brushes skin. A mild prickle on the neck. Nothing sharp enough to trigger alarm, nothing dramatic enough to stop movement. Sweat beads and runs under the collar, pooling at the wrists, gathering along the brow. The instinctive response follows immediately and without thought. You wipe your face. You clear your eyes. You smear what is already on you across the most vulnerable tissue you have. Venomous caterpillars do not need to bite. They do not chase or strike. Their defense is passive, distributed, and extraordinarily persistent. The spines that coat their bodies, hollow, brittle, and loaded with toxins, are designed to break off at the slightest contact. A brush against a sleeve, a shoulder grazing a branch, a backpack strap dragged across bark. Each interaction transfers dozens, sometimes hundreds, of microscopic needles onto fabric and skin. They hitchhike silently, embedded in fibers, clinging to sweat-dampened cloth, waiting for the moment they are carried somewhere more sensitive. The rainforest amplifies this mechanism. Humidity keeps spines mobile and adhesive. Heat opens pores and increases blood flow near the skin's surface, accelerating inflammatory response. Movement ensures constant redistribution. A caterpillar never needs to be touched directly. The forest itself becomes the delivery system. In the eye, the effect is immediate and punishing. Burning flares across the surface as venom disperses through tear fluid. Swelling begins almost at once, the tissues reacting aggressively to foreign bodies that cannot dissolve or wash away easily. Every blink becomes abrasive, the sensation unmistakably gritty, as if sand has been poured under the eyelid. Vision collapses into haze, not because the eye is irreparably damaged in that instant, but because tears, inflammation, and involuntary muscle contraction overwhelm clarity. The eye tries to protect itself by shutting down. Blinds fast does not mean permanent loss, but it does mean functional blindness at the worst possible time. Depth perception fails. Peripheral awareness disappears. In a forest where footing is unstable and obstacles are constant, losing clear vision even briefly can cascade into injury. A misstep sends weight onto a root slick with algae. A hand reaches out blindly and finds thorns or sap. Pain stacks on pain, confusion feeding urgency, urgency feeding mistakes. The real cruelty of this mechanism reveals itself after the first wave subsides. Unlike venom delivered by a bite or sting, caterpillar spines do not leave once the initial contact is over. They linger. They remain embedded in clothing fibers, trapped in towel loops, clinging to backpack straps, cuffs, and collars. Every time you touch those surfaces, you re-expose yourself. Every time you wipe sweat, scratch an itch, or rub an eye, you transfer more spines. The environment becomes contaminated, and without deliberate intervention, the cycle repeats. This aftershock phase is where most people lose control of the situation. The burning fades slightly, only to surge again minutes later. The eye seems to improve, then abruptly worsens. Confusion sets in. Wasn't it getting better? The answer is simple and unforgiving. You are still carrying the weapon. Biologically, this strategy is devastatingly effective. Venomous caterpillars evolved in ecosystems crowded with predators, birds, mammals, reptiles, all of which rely on mouths, snouts, or eyes to investigate prey. A defense that targets those areas without requiring active engagement shifts the balance entirely. The caterpillar does not need speed, strength, or awareness. It only needs to exist in the right place, covered in detachable deterrents that teach predators to keep their distance after a single encounter. Different species deploy this strategy in different ways. Some caterpillars, like those in the genus Lonomia, possess spines that deliver toxins capable of systemic effects when large numbers penetrate skin, interfering with blood clotting and causing internal bleeding. Others focus on intense, localized pain and inflammation, enough to incapacitate without risking lethal escalation. In all cases, the spines are structurally similar, fragile shafts that fracture cleanly, optimized to lodge in tissue and resist removal. Under magnification, these spines reveal their purpose. Tiny barbs anchor them in place. Hollow channels deliver venom directly into the surrounding tissue. The body's attempt to flush them out, tears, mucus, inflammation, often worsens the sensation, increasing pressure and spreading irritants rather than resolving them. The eye, exquisitely sensitive and poorly armored, becomes the perfect target not by design of the caterpillar, but by inevitability of human behavior. What makes this danger especially insidious is how ordinary the triggering actions are. No reckless handling, no deliberate contact, just routine movement through vegetation, followed by the most human reflex of all, touching your own face. Sweat, in this context, is not just discomfort. It is a vector, dissolving and redistributing venom, encouraging wiping, amplifying exposure. There is an ecological irony here. Caterpillars are often dismissed as juvenile forms, incomplete, waiting to become something else. In reality, this life stage is where many species are most chemically defended. Adults may rely on flight, camouflage, or mimicry. Larvae must remain exposed, feeding constantly to fuel metamorphosis. Chemical armor compensates for immobility. The forest recognizes this balance and responds accordingly. Predators learn quickly which textures and silhouettes to avoid. Bright colors, spines, tufts, signals layered atop one another to reinforce the message. For humans who did not evolve alongside these systems, the signals are easy to misread. A fuzzy caterpillar looks soft. A branch looks clean. A shirt sleeve feels safe. The lesson is delivered only after contact, and by then, the mechanism is already complete. Cleaning becomes the turning point. Until hands are washed thoroughly, until clothing is changed and rinsed, until towels and gear are isolated, the spines continue to circulate. This is why pain seems to persist beyond reason. It is not ongoing venom release from the caterpillar. It is repeated self-contamination. The forest is not attacking you again. You are carrying the forest with you. From a broader ecological perspective, this mechanism shapes behavior across species. Animals that learn to avoid spiny caterpillars gain a survival advantage. Those that do not pay the price quickly. Birds have been observed carefully stripping caterpillars of spines before consumption, a learned behavior passed through generations. Parasitoid wasps evolve strategies to bypass defenses, laying eggs in precise locations. Every adaptation creates a counter-adaptation, a living network of cause and effect woven into the forest's fabric. Human encounters sit awkwardly within this system. We are large, mobile, and technologically capable, yet behaviorally vulnerable. Our hands move faster than our judgment. Our faces remain unprotected. Our assumptions override caution. Venomous caterpillars exploit none of this intentionally. They simply persist in an environment that punishes inattention. As swelling recedes and vision returns, the forest resumes its neutral stance. Leaves drip. Insects hum. Light shifts. Nothing appears altered. Yet something fundamental has changed. Movement slow. Hands hesitate before wiping sweat. Clothing is handled with care. The lesson embeds deeper than the spines ever could. This is how the rainforest teaches. Not with spectacle, but with consequences that unfold through ordinary actions. You do not have to touch the danger directly. You only have to carry it to the wrong place. The rainforest does not announce danger with movement or sound. It hides it in stillness, in moisture, in the thin film left behind when life brushes past life. The scene opens low to the ground, where the Amazon floor breathes, leaf litter layered in decay, moss holding water like a sponge, and broad leaves sagging under the weight of constant humidity. Everything here is wet, even when it looks dry. Even the air clings. You move carefully, or you think you do, placing your hand against a trunk slick with algae, steadying yourself on a vine, wiping sweat from your brow because the heat never lets go. This is the most relatable trap in the rainforest, and the most underestimated, the reflex to touch, to wipe, to rub, to clear your vision so you can keep moving. Somewhere in this mosaic of green, no larger than a thumb, a poison dart frog sits motionless on a leaf. It does not stalk. It does not flee. It advertises itself openly, its skin glowing in impossible colors, electric blues, molten yellows, warning reds, like a signal flare against the jungle's muted browns and greens. These colors are not beauty for beauty's sake. They are a biological contract written in pigment, telling predators exactly what will happen if boundaries are crossed. The frog's defense is not speed or strength, but chemistry. Its skin secretes alkaloid toxins derived from its diet. Ants, mites, beetles, compounds that its own physiology has learned to tolerate, store, and deploy without self-harm. This is not venom delivered by a bite or sting. This is poison designed for contact. The mistake most people make is imagining threat as intent. The frog does not chase you. It does not leap toward your face. It does not inject anything. The danger emerges only when human movement completes the circuit. A leaf brushed aside with bare fingers. A slick hand pressed to a trunk. A quick unconscious swipe across the cheek to clear sweat or rain from your eye. In that moment, toxin transfer happens quietly and efficiently, following the same physical laws that govern water on skin. The frog's poison does not leap from leaf to eye. You carry it there yourself. On camera, the chain is almost invisible. A hand moves through undergrowth, compressing leaves already coated in microscopic films of moisture and biological residue. Fungal spores, plant sap, insect secretions, and sometimes poison. Alkaloids are lipid-soluble, designed to penetrate cell membranes. They cling. When fingers close around a vine or push aside foliage, the compound adheres to the skin's oils. Sweat spreads it further, thinning it into a film. By the time the hand rises toward the face, the danger is already distributed across the fingertips. The eye is not protected like the rest of the body. Its tissues are delicate, richly innervated, and designed for transparency rather than defense. When poison reaches the ocular surface, the response is immediate and overwhelming. Blinds fast does not mean permanent blindness in most cases, but it does mean sudden sensory overload. A searing burn spreads across the eye as pain receptors fire in rapid succession. Tears flood the surface, not as a defense mechanism strong enough to neutralize the toxin, but as a reflexive attempt to dilute and flush it. Eyelids clamp shut in involuntary spasm, the muscles contracting hard enough to ache. Vision collapses into blur, not because the eye is damaged, but because swelling, tearing, and muscle contraction make clear focus impossible. The rainforest does not pause while this happens. Roots twist underfoot. Mud gives way without warning. The canopy filters light into shifting patterns that already challenge depth perception. Losing vision here is not an inconvenience. It is a destabilization of the entire sensory system. Balance depends on sight more than most people realize, especially in complex terrain. As pain intensifies, the instinctive response is to rub harder, to force the eye open, to wipe away the tears that feel like the problem. This is the critical error. Rubbing does not remove the toxin. It drives it deeper into the tissues, spreads it across a larger surface, and introduces it to the tear ducts, where it can reach sensitive internal membranes. This is how a non-lethal encounter escalates. Pain increases, vision worsens, panic sharpens, foot placement becomes sloppy. A slip on wet clay sends the body sideways. A fall into shallow water raises the risk of secondary injury or infection. The frog never moves. The toxin does exactly what evolution shaped it to do: discourage contact by making the experience unforgettable. From the frog's perspective, this system is elegant. Poison dart frogs evolved their defenses not to kill indiscriminately, but to survive in an ecosystem dense with predators. Birds, snakes, mammals all learn quickly that bright coloration equals consequence. Some predators, like certain snakes, have evolved partial resistance, turning a once absolute defense into a selective filter that shapes who can hunt whom. This arms race has refined toxin potency, storage, and skin permeability over millions of years. The frog's survival depends on predators making mistakes once, not twice. What often goes unrecognized is how tightly this defense is linked to the frog's environment. These toxins are not produced from nothing. They are acquired through diet, meaning captive-bred frogs raised without access to specific insects lose much of their toxicity over time. In the wild, the rainforest acts as a chemical factory, producing alkaloids through plant-insect interactions that frogs tap into. The poison is not just a property of the animal, it is a property of the ecosystem itself, circulating through trophic levels like an invisible currency. Humidity amplifies this system. Moisture keeps toxins mobile, prevents them from drying or degrading quickly, and increases skin absorption rates. Heat opens pores, increases blood flow, and accelerates physiological responses. What might be a mild irritant in a dry environment becomes a serious sensory assault here, not because the poison is stronger, but because the conditions are optimized for transfer. There is a deeper lesson embedded in this mechanism. The rainforest rarely punishes curiosity directly. It punishes shortcuts. The instinct to move fast, to clear vision without stopping, to prioritize momentum over caution, that is what completes the chain. Indigenous peoples who move through these forests daily learn early to respect stillness, to wash hands deliberately, to keep fingers away from the face, to stop moving before addressing discomfort. These behaviors are not superstition. They are survival protocols shaped by generations of close observation. On a biological level, the eye's response tells a story of evolutionary trade-offs. Vision is prioritized so heavily in primates that the organ sacrifices durability for sensitivity. Pain receptors are abundant because damage must be avoided at all costs. The violent reaction to toxins is not weakness. It is an alarm system screaming for immediate cessation of exposure. The tragedy is that human instinct often interprets that alarm as something to fight rather than heed. As the pain slowly subsides, minutes stretching into what feels like hours, tears eventually flush much of the compound away. Swelling recedes. Vision returns in fragments, edges sharpening last. The frog remains where it was, still broadcasting its warning colors into the understory. The encounter ends without blood, without pursuit, without drama visible from a distance. Yet it leaves behind a profound recalibration of behavior. This is the real power of contact poisoning. It does not rely on aggression. It relies on participation. The rainforest offers countless such mechanisms: fungal spores that irritate lungs, plant saps that blister skin, insects that deliver delayed reactions. Poison dart frogs simply make the lesson unmistakably clear. You do not have to be attacked to be harmed. You only have to move carelessly through a system that assumes you are paying attention. In the end, the blindness is temporary, but the vulnerability it exposes is permanent. The forest does not meet you halfway. It does not adapt to your habits. It waits, patient and chemically precise, for the moment you forget that every surface here is alive with consequence. The sound arrives before the sensation. A thin, almost electrical whine, cutting through the layered noise of the rainforest, so faint it barely registers as a threat. Mosquitoes do not announce themselves with spectacle. They arrive incrementally, testing boundaries, sampling air currents, riding carbon dioxide plumes and body heat like invisible highways. By the time you notice them, the interaction has already begun. The forest is built for them. Warm, humid air slows evaporation and keeps skin moist. Standing water collects in leaf axils, hoofprints, fallen fruit husks, and rotting logs, creating thousands of micro-nurseries invisible at human scale. Mosquitoes emerge in pulses, synchronized with rainfall, temperature, and moonlight. Each generation timed to exploit moments when vertebrates are most exposed. They are not random irritants. They are products of an ecosystem optimized for blood-feeding efficiency. The bites that matter most are rarely the ones you feel immediately. Around the eyes, skin is thin, richly vascularized, and densely innervated. Mosquitoes target these zones not out of malice, but because blood flow is high and defenses are low. A brief probe, a tiny injection of saliva containing anticoagulants and immune-modulating compounds, and the insect lifts away unnoticed. The chemistry lingers. Swelling begins quietly. Fluid accumulates beneath the eyelid, drawn in by inflammatory signals responding to foreign proteins. At first it feels like pressure, a subtle heaviness. Then the eyelid thickens, stretching skin that was never meant to accommodate volume. Tears follow, the lacrimal glands responding to irritation and distortion. Vision softens on that side, edges losing definition. This is where the mechanism accelerates. The itch arrives next, deep and insistent, driven by histamine release rather than surface irritation. It does not feel like something on the skin. It feels like something under it. Rubbing becomes almost involuntary. Fingers press into swollen tissue, smearing sweat, skin oils, dust, and whatever else has accumulated on the hands across the eye and lid. Each rub worsens the inflammation, increasing vascular leakage and swelling. Blind's fast here is brutally literal. One eyelid can swell shut completely, sealing the eye behind puffed tissue that refuses to open. The other eye, overworked and constantly rubbed, becomes blurred by tears and irritation. Vision does not disappear all at once. It degrades asymmetrically, unpredictably, forcing the brain to compensate in real time with mismatched inputs. Depth perception collapses first. The forest floor, already deceptive with its layers of leaf litter and shadow, becomes unreadable. Roots that were once obvious merge into background noise. Small changes in elevation vanish until the foot meets them too late. Balance falters as the vestibular system struggles to reconcile conflicting visual cues. Mosquitoes do not stop biting during this process. They continue to land, drawn to heat and sweat, adding new irritation to old wounds. Each bite compounds inflammation, not just locally, but systemically. Scratching spreads saliva proteins across skin, increasing immune response and accelerating swelling. The face becomes a focal point of discomfort, commanding attention away from everything else. This is the trap chain unfolding in real time. Reduced vision leads to a wrong step. A foot slides on damp clay. Weight shifts suddenly. Hands shoot out to break the fall, palms scraping against bark, rock, or thorny vegetation. Skin breaks. Blood beads. Now the forest's microbial world enters the equation. Bacteria, fungi, parasites waiting on every surface. Sweat carries them into cuts. Mud seals them in. The mosquito's role ends long before this. It does not follow. It does not escalate. It simply triggered a physiological reaction that narrowed perception at the wrong moment. Ecologically, this mechanism is elegant. Mosquitoes evolved to exploit vertebrate immune systems, not overpower them. Their saliva is a biochemical toolkit designed to keep blood flowing while evading detection. Swelling and itching are side effects of immune recognition, not direct attacks. Yet those side effects are powerful enough to alter behavior dramatically. In many rainforest animals, this reaction is managed differently. Thick fur, feathers, or behavioral adaptations reduce facial exposure. Some species time activity to avoid peak mosquito hours. Others use mud, plant oils, or communal grooming to mitigate bites. The ecosystem has responded to mosquitoes with a wide range of counter-strategies refined over evolutionary time. Humans arrive without those adaptations. Our faces are exposed. Our skin is thin. Our instinct is to rub, to scratch, to wipe away discomfort immediately. In an environment where vision is critical for safe movement, this instinct becomes dangerous. The irony is that the mosquito's bite is medically trivial in isolation. The swelling is temporary. The irritation fades. But the timing is everything. Losing effective vision for even a few minutes in dense terrain is enough to create cascading failures. Falls become more likely. Cuts become deeper. contamination becomes inevitable. This is where mosquitoes surpass their reputation as mere nuisances. They are not just disease vectors or sources of irritation. They are agents of sensory disruption. They interfere with the most important survival tool humans rely on in complex environments: sight. The swelling around the eye is not uniform. Gravity pulls fluid downward, distorting the lid unevenly. Tears spill across the cheek, blurring the lower visual field. Blinking becomes rapid and incomplete, smearing moisture rather than clearing it. The brain compensates by over-relying on the remaining clear eye, increasing fatigue and narrowing awareness even further. As movement continues, the forest offers no mercy. Branches at face height go unseen until they strike. Sharp leaf edges scrape skin. Insects crawl into newly opened cuts. Each new sensation competes for attention, fragmenting focus until the body is reacting rather than navigating. From a physiological perspective, this highlights how fragile human visual dominance really is. Vision is not just about eyes. It depends on stable posture, coordinated muscle control, and uninterrupted sensory input. Mosquito-induced swelling disrupts all three indirectly, without ever touching the eyeball itself. The aftermath often feels disproportionate. Why did something so small cause so much trouble? The answer lies in sequence, not severity. Mosquitoes excel at starting chains they never have to finish. They exploit predictable human reactions and let the environment amplify the consequences. As swelling eventually recedes and tears slow, clarity returns unevenly. One eye opens fully, while the other lags behind, stiff and tender. Depth perception rebuilds gradually. The forest looks unchanged, as if nothing happened. The mosquito population hums on, indifferent to the chaos it helped trigger. What remains is behavioral residue. Hands hover near the face, but hesitate. Eye protection feels suddenly valuable. Movement slows when vision falters, rather than speeding up. These adjustments are not fear responses. They are lessons learned through consequence. This chapter completes a pattern that runs through the entire series. Not all blindness comes from venom or trauma. Sometimes it comes from swelling, from immune reactions, from the body defending itself too aggressively in the wrong place. The mosquito does not need to blind you permanently. It only needs to close one eye and blur the other long enough for the forest to assert its rules. In the rainforest, danger rarely arrives as a single, overwhelming force. More often, it arrives as a small, irritating interaction that erodes perception step by step, until one wrong movement opens the door to everything else waiting nearby. The forest floor looks inert until you disturb it. A fallen log, silvered with rot and veined with fungus, appears lifeless, just another obstacle in a landscape already crowded with debris. When it shifts, when bark peels back and the darkness beneath is exposed, the ecosystem reacts instantly. Beetles scatter, antlines fracture and reform. Moist soil exhales the smell of decay. And somewhere in that sudden exposure, something that has been perfectly still becomes alert. The tarantula does not rush. It does not lunge. It turns slightly, just enough for its abdomen to angle toward the threat. This is the moment most people miss. There is no strike, no bite, no dramatic leap. What happens next is smaller, faster, and far more effective. A rapid flick of the hind legs sends a cloud of microscopic urticating hairs into the air, so fine they behave less like projectiles and more like dust. In the filtered light of the understory, they are invisible. There is no sound, no warning. The defense has already left the spider before the human brain registers that anything has gone wrong. Tarantulas evolved this mechanism not for combat, but for deterrence. Their urticating hairs are modified setae, specialized bristles with barbed tips that break off easily and embed aggressively into soft tissue. To predators with sensitive mucous membranes, mammals, birds, reptiles, these hairs are not just irritating, they are incapacitating. The spider does not need to injure. It only needs to create enough discomfort that the predator retreats and remembers. Evolution favors efficiency, and invisible shrapnel is efficient. In the rainforest, air movement is minimal under the canopy. Humidity is high, particles linger, and moisture helps these hairs stay suspended just long enough to find their target. Eyes are the most vulnerable point of entry. They are wet, exposed, and constantly adjusting to light. When the hairs make contact with the ocular surface, the effect is immediate and violent. The sensation is not a sting, but abrasion, like grinding fine glass into living tissue. Blinds fast is not metaphorical here. The eye reacts before conscious thought. Eyelids snap shut in a powerful reflex, driven by the trigeminal nerve-firing pain signals at full intensity. Tears surge, flooding the surface in an attempt to flush out the foreign bodies. Vision on that side collapses, not gradually, but all at once, overwhelmed by fluid, swelling, and involuntary muscle contraction. Depth perception fails instantly. In dense terrain, that loss alone is enough to turn a stable stance into a fall. The worst mistake comes next, and it is almost guaranteed. Rubbing feels instinctive, even logical. Something is in the eye, so you try to remove it. But urticating hairs are designed to defeat exactly that response. Each hair is tipped with microscopic barbs that anchor deeper when pressure is applied. Rubbing does not dislodge them. It drives them in, increases surface damage, and spreads them across a wider area of the eye and eyelid. What could have been a severe irritation becomes a sandpaper nightmare, every blink dragging barbed filaments across inflamed tissue. The forest does not stop while this unfolds. The ground remains uneven. Roots snake just below the leaf litter. Water pools where you cannot see it. With one eye effectively gone, balance falters. The brain struggles to reconcile conflicting sensory inputs. Pain screaming from one side, darkness where vision should be, and a constant urge to claw at the source of discomfort. This is how accidents compound. A twisted ankle, a stumble into thorny vegetation, a fall against a trunk slick with algae. The spider is already gone, retreating into its burrow, its defense deployed and its survival secured. From the tarantula's perspective, this interaction is entirely defensive. These spiders are not aggressive animals. They conserve energy, relying on ambush and patience rather than pursuit. Many species spend daylight hours hidden, emerging at night when humidity is highest and prey movement increases. Their large size and slow gait make them conspicuous, and without venom, potent enough to deter all predators, they evolved redundancy. The bite is a last resort. The hairs are the first line of defense, deployed at a distance, effective even without contact. What makes this mechanism particularly dangerous to humans is not its lethality, but its subtlety. People underestimate tarantulas because they move slowly and look cumbersome. They are labeled harmless compared to snakes or scorpions. This misclassification leads to risky behavior, handling, poking, relocating, or casually moving objects without protection. Boots left overnight become shelters. Gloves set on the ground collect more than just moisture. A hand reaches inside without looking. The spider reacts, not with malice, but with precision. There is a deeper biological story unfolding here. Urticating hairs are not universal among tarantulas. They evolved primarily in New World species, a response to specific predator pressures in the Americas. Old World tarantulas lack these hairs and rely more heavily on potent venom and threat displays. This divergence highlights how defense strategies are shaped by local ecological conditions. In environments where predators attack with snouts, beaks, or grasping limbs, airborne defenses that target eyes and respiratory passages offer a decisive advantage. The hairs themselves are marvels of microengineering. Under magnification, each one reveals a structure optimized for penetration and retention. They fracture cleanly at the base when flicked, ensuring maximum dispersal, and their barbs prevent easy removal once embedded. In skin, they cause itching and rash. In eyes, they trigger intense inflammation and, in severe cases, corneal damage that can persist for days or weeks. Medical literature documents instances where embedded hairs required surgical removal, not because the spider attacked, but because a human touched their face at the wrong moment. Heat and sweat amplify the danger. Moisture makes hairs adhere more readily to skin. Sweat spreads them across fingers and palms. The reflex to wipe eyes becomes almost irresistible as irritation builds. This creates a feedback loop. Discomfort drives rubbing, rubbing increases injury, and injury escalates panic. The mechanism does not rely on toxin or venom, only on physics and physiology working together. The tarantula's role in the ecosystem extends far beyond this moment of defense. As predators of insects and small invertebrates, they regulate populations that would otherwise explode. Their burrows aerate soil, creating microhabitats for other organisms. They are prey themselves, feeding birds, mammals, and even specialized wasps that exploit their biology in intricate life cycles. The urticating hairs are not a weapon of dominance, but a compromise, strong enough to deter, limited enough to avoid unnecessary escalation. For humans moving through these environments, the lesson is consistent with every other invisible hazard in the rainforest. Danger is rarely loud. It rarely announces itself. It waits for participation. Handling a slow spider, lifting a log without gloves, shaking out boots without looking, touching your face with contaminated hands. These are the steps that complete the chain. The spider does not need to be large, fast, or aggressive. It only needs to exist, armed with a defense honed by millions of years of selective pressure. When vision finally returns, when the pain dulls to a persistent ache and swelling recedes enough to open the eye, the environment looks unchanged. The log lies where it fell. The forest resumes its quiet motion. But the encounter leaves a lasting imprint on behavior. Movements become slower. Hands stay lower. Eyes are protected instinctively. This is the real function of the mechanism, not to injure permanently, but to teach instantly. In the rainforest, survival often depends on understanding that the most dangerous events do not look like attacks. They look like accidents that were never accidents at all, but consequences waiting patiently for a single careless touch. The forest floor is never still, but most of its movement is quiet enough to pass unnoticed. Leaves fall, rot, and dissolve into soil that seems soft until weight presses down and it shifts. Roots lace the ground in unpredictable patterns, their surfaces polished slick by moisture and microbial life. In this layered darkness, order emerges not from stillness, but from traffic. Thin green ribbons slide across the earth, arcing over roots, pouring down tree trunks, vanishing into holes no wider than a coin. These are leafcutter ant trails, highways of purpose so precise and constant that the forest itself bends around them. The danger begins the moment you intersect one. At first, it feels like nothing more than irritation. A few ants scatter underfoot. One crawls up a boot. Another brushes a calf. Then the trail reacts as a unit. Workers surge upward in waves, their movements synchronized not by sight, but by chemical alarm signals released instantly into the air and substrate. Bites follow in rapid succession, sharp, pinching sensations that strike ankles, shins, wrists, anywhere skin is exposed. Each bite is small, almost trivial on its own, but they do not arrive alone. They arrive everywhere. This is the panic moment. The body reacts before the mind has time to assess. Muscles tense. Balance shifts. Hands flail instinctively, trying to brush insects away, trying to regain control of space that has suddenly become hostile. In the heat and humidity of the forest, sweat is already flowing freely, carrying dust, grit, plant fragments, and whatever else the skin has collected along the way. As bites accumulate, the reflex to wipe the face becomes almost irresistible. Sweat stings. Ants crawl near the eyes. The hand comes up fast. This is where the mechanism completes. Leafcutter ants are not venomous in the way snakes or spiders are, but their mandibles are precision tools, evolved to shear plant tissue cleanly and efficiently. When they bite skin, they create dozens of tiny cuts, microscopic breaches that barely bleed but burn immediately. These cuts disrupt the skin's protective barrier, turning sweat from a neutral byproduct into a delivery system. Sweat now carries salt, organic acids, soil particles, and ant secretions across broken skin and toward the eyes. An eye wipe that would be harmless under normal conditions becomes an abrasive smear. Salt stings raw nerve endings. Grit scratches the corneal surface. Ant-derived irritants mix into the tear film. The sensation escalates instantly from discomfort to acute pain. Tears surge. Vision blurs. Eyelids blink hard and fast, trying to clear an irritant that is being spread with every movement. Blinds fast is not hyperbole here. The loss of vision is functional and immediate. It is not that the eyes are damaged beyond recovery in that moment, but that the combination of tearing, pain, and involuntary blinking makes focused sight impossible. Depth perception collapses. Peripheral awareness narrows. In a terrain already hostile to stable footing, this sudden sensory loss is enough to tip the balance from control to chaos. The forest does not pause. Roots still wait at ankle height. The ground still slopes unpredictably. Leaf litter still conceals holes and slick patches of mud. With eyes forced shut or half-blind, the body compensates poorly. Steps become shorter and more frantic. Weight shifts erratically. A stumble sends a foot sliding. A hand reaches out blindly and meets bark sharp with thorns or coated in irritant sap. The initial threat, ant bites, has already receded in importance. The cascade has begun. From an ecological perspective, this outcome is an accident, not an intention. Leafcutter ants do not defend territory by targeting eyes. They defend trails and nests through overwhelming numbers and relentless contact. Their power lies in scale. A single ant is insignificant. 100 ants responding to an alarm signal become an environmental force. The forest floor itself seems to rise up and bite back. These ants are among the most influential organisms in the rainforest, not because they attack large animals, but because they reshape ecosystems. Their trails carve lasting scars into soil. Their nests aerate the ground, alter nutrient cycles, and support complex fungal agriculture systems that rival human farming in efficiency. They harvest leaves not to eat directly, but to cultivate symbiotic fungi that feed entire colonies. This system requires absolute precision and defense. Any interruption, whether by predator or careless footstep, is met with immediate response. Human skin is not a target the ants evolved to exploit, but it is vulnerable in ways that mirror their natural enemies. Soft tissue, moist surfaces, exposed sensory organs. When humans blunder into ant highways, they inadvertently mimic the behavior of animals that attempt to raid nests or disrupt trails. The ants respond as they always have, with bites delivered en masse, designed to drive the intruder away through irritation and pain rather than lethal force. The micro-cuts themselves are deceptively minor. Individually, they heal quickly. Collectively, they transform the skin's chemistry. Sweat entering these tiny wounds burns, amplifying discomfort and urgency. When that same sweat is transferred to the eyes, the effect multiplies. The eye's surface is exquisitely sensitive, prioritizing clarity and responsiveness over toughness. It reacts to any foreign substance with maximum force. Tears flood the area not to soothe, but to flush. Blinking accelerates, but blinking also spreads irritants across the cornea. This is why vision loss feels disproportionate to the original injury. No single ant caused it. No single bite explains it. The blindness is emergent, a product of many small factors aligning in the wrong order. Distraction leads to flinching. Flinching leads to face touching. Micro-cuts turn sweat into an irritant. The eye, caught in the middle, shuts down. There is an additional layer to this mechanism that often goes unnoticed. Panic itself alters physiology. Heart rate spikes. Breathing becomes shallow and rapid. Sweat production increases. Pupils dilate, then constrict erratically as the eyes attempt to adapt to pain and tearing. These changes worsen visual instability and reduce fine motor control. The harder the body tries to regain equilibrium, the more it undermines itself. In animals that live alongside leafcutter ants, behavior has evolved to avoid this cascade entirely. Many species learn to recognize trails visually and by scent, stepping carefully over or around them. Some predators exploit ant highways indirectly, using them as indicators of nutrient-rich areas without ever crossing them. The ants broadcast their presence constantly. The forest listens. Humans, unfamiliar with these signals, rely on reaction rather than anticipation. By the time ants are noticed, contact has already occurred. The instinct to brush them away is strong, but it feeds directly into the danger. Stillness, counterintuitively, would reduce harm, allowing ants to disperse without provoking further bites. But stillness is difficult when pain arrives in dozens of sharp points at once. As vision returns, slowly, unevenly, the ants recede as quickly as they appeared. The trail reforms, traffic resuming within minutes, as if nothing happened. The forest resets. Only the human carries the memory, imprinted not as fear of ants, but as a new understanding of scale. How something so small can disrupt balance, perception, and movement with no venom, no toxins, no pursuit. This chapter reveals a broader truth about rainforest danger. Not all blindness comes from poisons or spines. Sometimes it comes from distraction layered onto environment, from the accumulation of minor injuries amplified by instinctive responses. The ants did not attack the eyes. The eyes were caught in the aftermath of a system doing exactly what it evolved to do. In the end, leafcutter ants teach a lesson that echoes throughout the forest. Pay attention to patterns. Respect traffic. Do not underestimate the collective power of small forces acting together. The rainforest rarely overwhelms with a single blow. More often, it blinds you just long enough for gravity, terrain, and your own reactions to finish the work. The encounter usually happens at the edge of comfort, where land and water trade dominance and footing is never guaranteed. The air is heavy, saturated with heat and moisture, carrying the low smell of rot and algae. Roots rise from the ground like ribs, slick with biofilm, weaving an obstacle course that demands attention with every step. Near these margins, drainage ditches, riverbanks, irrigation canals, flooded trails, something squat and unhurried waits in plain sight. The marine toad does not hide. It does not need to. Its defense is already active, coating its skin in a chemical message that says exactly what it is and why it should not be touched. The most persistent myth surrounding this animal is also the most misleading, that it somehow sprays toxin into the eyes of those who approach. This framing turns a passive defense into an imagined act of aggression and obscures the real mechanism entirely. The marine toad does not aim. It does not project. It simply exists, its skin and glands primed to punish contact. The danger emerges only when a human completes the transfer. The toad's body is built around chemical deterrents. Along the shoulders and behind the eyes sit the parotoid glands, large, swollen structures that look almost anatomical, like misplaced organs pressing outward beneath the skin. These glands produce and store a milky secretion rich in bufotoxins, a complex mixture of cardiac glycosides, biogenic amines, and other compounds designed to disrupt physiological systems. For predators that bite, the effect can be lethal. For those that merely touch, the consequences are immediate and unforgettable. Handling is the turning point. A toad lifted from a trail, nudged aside with bare hands, or grabbed in a moment of surprise responds reflexively, tensing its body and exuding toxin onto the skin's surface. The secretion is sticky, designed to adhere. It coats fingers, palms, and sweat-slicked skin with ease. In humid environments, where hands are already wet and pores open, the transfer is efficient and thorough. At this stage, nothing hurts yet. There is no dramatic signal that something has gone wrong. The mistake feels incomplete. That changes when the hand rises toward the face. Eyes are magnets for this kind of danger, not because they attract toxins, but because humans constantly touch them without awareness. Sweat stings, bugs buzz, contact lenses dry out, fingers move upward, carrying whatever they have encountered most recently. When marine toad toxin reaches the eye, the response is violent and instantaneous. Severe irritation floods the sensory field, a burning that feels both chemical and abrasive, as if the eye has been soaked in something corrosive rather than merely exposed. Tears erupt, not gradually, but in a sudden surge that blurs vision beyond recognition. Eyelids clamp shut in a protective spasm, so strong it can feel impossible to override. Blinds fast is not exaggeration. Functional blindness occurs within seconds. The eye cannot remain open long enough to focus. Tears distort light. Muscles contract involuntarily. Even if the toxin does not cause lasting damage, the effect is total in the moment that matters most. Sweat makes everything worse. It spreads the toxin across the face, thins it into a film that can creep into both eyes, and encourages repeated wiping as discomfort escalates. Contact lenses amplify the problem further, trapping chemicals against the corneal surface and prolonging exposure. Instead of flushing the toxin away, blinking and tearing redistribute it, smearing irritation across a larger area and extending the duration of pain. From the toad's perspective, this outcome is exactly what evolution intended. Marine toads evolved in environments dense with predators that rely on mouths, eyes, and mucous membranes to test prey. A defense that targets those vulnerabilities without requiring a chase or a bite confers enormous survival advantage. The toad does not waste energy fleeing. It does not need camouflage. It announces its presence openly, trusting chemistry to do the rest. The ecological story behind this mechanism runs deep. Marine toads are generalists, capable of thriving in disturbed habitats where many amphibians fail. Their toxin protects them not just from predators, but from competition. Animals that might otherwise exploit the same food sources learn quickly to avoid them. In regions where marine toads have been introduced, the imbalance can be severe, with native predators suffering fatal poisoning after a single bite. The toxin does not discriminate between naive wildlife and curious humans. The human cost, however, rarely comes from ingestion. It comes from proximity and misjudgment. The belief that the toad is slow, clumsy, or harmless encourages contact. The belief that danger requires intent encourages carelessness. In reality, the toad's defense is already deployed before anyone touches it. The moment skin meets skin, the mechanism is complete. What follows is not just pain, but risk. Vision loss near water transforms stable ground into a hazard field. Routes that were manageable become traps. A step too far sends a foot into a hidden hole filled with mud or water. A stumble forward results in hands instinctively reaching out, palms scraping against sharp bark, thorns, or broken stems. Cuts open pathways for infection in an environment where bacteria and fungi thrive. The original exposure may not be life-threatening, but the cascade of consequences can be. This is where the survival angle becomes clear. Losing vision, even temporarily, in complex terrain is not a minor inconvenience. It disrupts balance, orientation, and situational awareness all at once. The body's protective reflexes, closing the eyes, pulling inward, curling forward, conflict with the demands of staying upright and moving safely. Panic tightens muscles and shortens steps, increasing the likelihood of falls. In wet environments, a single misstep can mean sliding into water where footing disappears entirely. The irony is that the marine toad does not benefit from escalation. Its toxin is not designed to chase or pursue. Once contact ends, the toad is content to remain still, trusting that the lesson has been delivered. The pain fades gradually, with proper flushing and time. Vision returns in fragments, clarity creeping back as swelling subsides. Yet the environment never changed. Only the margin for error did. From a physiological standpoint, the eye's extreme reaction underscores its vulnerability. The cornea is densely innervated, prioritizing sensitivity over durability. Any chemical insult triggers a maximal response aimed at immediate protection, even at the cost of temporary blindness. This trade-off works well when threats are rare and avoidable. In the rainforest, where chemical defenses are common and surfaces are shared by countless organisms, it becomes a liability. The marine toad's glands themselves are a study in evolutionary compromise. Producing toxin is metabolically expensive, yet the payoff is immense. The glands regenerate slowly, encouraging the toad to avoid unnecessary discharge. This is why handling often triggers secretion, while casual proximity does not. The system is tuned to respond precisely when contact suggests imminent danger. The toad does not waste its defense on shadows or vibrations. It waits for touch. For humans, understanding this distinction matters. The toad is not an aggressor. It is a passive node in a chemical network that rewards distance and punishes contact. Misunderstanding the mechanism leads to the wrong behaviors: panic, rubbing, repeated touching that deepen exposure rather than resolve it. The broader ecological lesson mirrors those found throughout the rainforest. Many of the most effective defenses are invisible until activated by human habit. They rely on transfer rather than force, on chemistry rather than speed. The environment assumes competence, not forgiveness. It offers clear signals to those adapted to read them and harsh corrections to those who are not. As the episode ends, the toad remains where it was, its parotoid glands still full, its posture unchanged. Night insects resume their chorus. Water reflects broken light through branches overhead. The landscape appears calm, indifferent. Yet the memory of the encounter lingers in altered behavior. Hands kept away from the face, eyes shielded instinctively, movements slowed near water and roots. This is the real function of the mechanism: not to blind permanently, not to injure needlessly, but to enforce distance in a world where touch is often automatic and consequences are rarely immediate. The marine toad does not spray danger into the world. It waits for the world to come to it, then lets chemistry do what muscle never could. The rainforest has a way of shrinking threats until they disappear into the background. Leaves overlap, shadows stack, and movement becomes so constant that the mind filters most of it away. In this visual noise, size feels like a reliable metric. Big animals matter. Small ones fade into irrelevance. This assumption is one of the forest's most reliable traps, and the assassin bug is built to exploit it. You do not notice the insect until the moment it decides you are part of the landscape. It waits on bark, on leaf undersides, on the seams where vines meet trunks, its body broken into angles that mimic thorns, lichen, or dried plant scars. Some species coat themselves in dust, plant fibers, even the remains of their prey, becoming indistinguishable from the surface they inhabit. This is not passive camouflage. It is an active hunting strategy, refined for ambush. Assassin bugs are predators first, defenders second, and every part of their anatomy reflects that priority. The proboscis is the key. Folded neatly beneath the head, when at rest, it looks harmless. Just another mouthpart on an insect already easy to dismiss. In reality, it is a hardened syringe capable of piercing insect exoskeletons and injecting a cocktail of enzymes that liquefy tissue from the inside. Against prey, the effect is immediate and terminal. Against human skin, the outcome is different, but no less instructive. The bite comes without warning. There is no buzz, no dramatic movement, no escalation. One moment the insect is part of the background. The next, pain detonates at a single point. It is sharp, deep, and disproportionate, far more intense than expected from something so small. The sensation is not the mild irritation of a mosquito or the fleeting pinch of an ant. It is a burning puncture that radiates outward, accompanied by a pressure that feels wrong, invasive, as if something has been forced into the body rather than merely breaking the surface. The assassin bug does not need to inject venom meant for humans. The same digestive enzymes it uses to pre-digest prey are more than sufficient to trigger a violent response in mammalian tissue. This is the small predator, big pain moment, and it lands hard. The body reacts instantly. Muscles tense. Breath catches. Attention collapses inward, fixating on the injury. Hands move before thought can intervene, slapping, scratching, grabbing at the site of the bite in a reflexive attempt to remove whatever caused it. The insect is often already gone, dropping away or freezing back into invisibility, its job done. The human response, however, has only begun. Pain accelerates behavior. Heart rate spikes. Sweat surges, driven by heat and stress. The bite throbs, swelling beginning around the puncture as the immune system floods the area with inflammatory signals. The urge to touch intensifies, not just to scratch the bite, but to wipe sweat from the face, to clear vision, to regain control over a body that suddenly feels compromised. This is where the mechanism turns. Hands that have just been pressed into bark, leaf litter, soil, or the insect itself rise toward the face. Whatever the assassin bug carried on its body, environmental bacteria, plant residues, traces of its own enzymatic saliva, now coats the fingers. Sweat spreads it further, thinning contaminants into a film. When those fingers reach the eye, the transfer is effortless. The eye responds immediately. Burning blooms across the surface, distinct from the original bite, but no less intense. Tears erupt, blurring vision in seconds. Eyelids clamp shut, muscles contracting hard enough to ache, as if the body is trying to erase the sensory input entirely. Focus collapses. Depth perception vanishes. The world narrows to pain and motion without clarity. Blinds fast is not a metaphor here. Functional blindness sets in not because the eye is destroyed, but because it is overwhelmed. Swelling, tearing, and involuntary blinking make vision unusable on that side. The brain, already stressed by pain and adrenaline, struggles to compensate. Balance falters. Footing becomes uncertain. The aftershock unfolds quickly. The bite continues to swell, radiating heat and discomfort that demands attention. The eye burns with every blink, each movement grinding irritants across sensitive tissue. Focus fractures, pulled constantly between competing signals of distress. The forest, indifferent to this internal chaos, remains as complex and hazardous as ever. Roots still rise at ankle height. Branches still jut at eye level. The ground still shifts underfoot. Losing visual stability in this environment is not a minor inconvenience. It is a serious survival problem. A misstep sends weight onto a slick surface. A stumble forces hands out again, palms meeting rough bark or thorned vines. Each contact introduces new irritants, new opportunities for contamination. The cascade feeds itself. From the assassin bug's perspective, this outcome is incidental but advantageous. These insects evolve to immobilize prey quickly and decisively. Their bite is not meant to deter large animals, but it does so effectively because of its intensity. A predator that learns to associate that kind of pain with a particular shape or texture is less likely to interfere again. The bug does not chase. It does not escalate. It relies on memory. Ecologically, assassin bugs occupy a critical niche. They regulate populations of other insects, many of which are agricultural pests or disease vectors. Some species specialize in hunting spiders, others in ambushing ants or termites, inserting themselves into the most active currents of the forest's invertebrate economy. Their success depends on stealth and precision, not durability. They are not built to withstand being crushed or bitten in return. The bite is their insurance policy, a way to create space instantly. Human encounters are accidents of scale. To the bug, a human is not prey, but neither is it a non-entity. Warmth, vibration, and pressure trigger defensive or opportunistic bites. The insect does not distinguish between a finger and a caterpillar segment. It reacts according to rules written long before humans arrived. The physiological response in humans reveals another layer of vulnerability. Pain is a powerful attention hijacker. It narrows perception, accelerates movement, and reduces fine motor control. These effects are adaptive when escaping immediate threats, but counterproductive in environments where precision matters. Scratching, wiping, flinching, these are all attempts to regain comfort quickly, but they sacrifice caution in the process. The eye, once again, becomes collateral damage. It is exposed, moist, and neurologically prioritized. Any contaminant introduced there triggers maximum response. The irony is that the assassin bug never targets the eye. The blindness is self-inflicted, the result of reflexes acting faster than understanding. Medical outcomes from assassin bug bites vary. Most resolve without lasting damage, though pain can persist for hours or days. Secondary infections are possible if wounds are contaminated. The eye irritation typically subsides with proper flushing, but until it does, the risk window remains open. The forest does not care whether the cause was venom, enzyme, or dirt. Loss of vision is loss of vision, regardless of origin. Animals that coexist with assassin bugs behave differently. Many avoid surfaces where these insects are common. Some birds peck cautiously, testing before committing. Other insects recognize chemical cues and steer clear. The forest has integrated the bug's presence into its behavioral map. Humans, lacking that context, rely on reaction rather than recognition. As swelling gradually subsides and tears slow, vision returns in fragments. Edges sharpen. Depth perception reassembles. The world snaps back into focus as if nothing happened. The assassin bug is nowhere to be seen, having long since resumed its role as a silent regulator of insect life. What remains is a recalibration of attention. Hands hesitate before touching bark. Sweat is tolerated rather than wiped immediately. Small insects are no longer dismissed outright. The lesson is subtle but durable. In the rainforest, scale does not predict consequence. This chapter is not about venom or lethality. It is about how pain, even from the smallest predator, can collapse focus and set off a chain of errors far more dangerous than the bite itself. The assassin bug does not need to blind you. It only needs to hurt you badly enough that you do the rest on its behalf. The web is easy to miss because it is not meant to be seen. It occupies the negative spaces humans ignore. Under a log lifted too quickly, inside a hollow root, beneath the rim of a rock where shade never leaves. The black widow does not advertise itself the way brightly colored animals do. Its warning is quiet, architectural, suspended in irregular strands that catch debris but not attention. This spider survives by being overlooked, by existing at the margins of perception where hands move without eyes ever following. The encounter begins with contact, not spectacle. A hand reaches into shadow. Fingers brush silk. There is a brief, sharp prick that feels almost insignificant compared to what people expect from venomous animals. No dramatic collapse. No immediate crisis. The spider drops away or freezes, its role finished in an instant. What follows is not an attack on the senses, but a slow destabilization of the body itself. Black widow venom is not designed to blind. It is neuroactive, targeting synaptic transmission and triggering a cascade of physiological responses that unfold over time. Muscles begin to tighten involuntarily, first near the bite, then spreading outward in waves that feel like deep cramps twisting beneath the skin. Sweat breaks out abruptly, soaking clothing and skin regardless of ambient temperature. Nausea creeps in, subtle at first, then insistent. The body enters a state of internal conflict, systems firing too hard and too fast, demanding attention from every direction at once. This is where the real danger emerges, not from the venom alone, but from what it does to behavior. Pain narrows focus. Cramping disrupts posture and balance. Sweating becomes relentless, pouring down the face, into the eyes, across the lips. The instinct to wipe becomes constant, almost compulsive, driven by discomfort rather than logic. Hands rise again and again, smearing sweat across the brow, clearing vision for a moment before it blurs again. Coordination slips, not catastrophically, but enough to matter in a complex environment. The blind's fast angle here is not about toxin in the eye. It is about interference. Sweat carries everything the hands have touched: dust, soil, spider silk, microscopic debris, into the most sensitive tissue on the body. Each wipe introduces a new irritant. Tears follow, blurring vision just as muscle cramps tighten and nausea weakens resolve. Eyelids flutter and clamp shut intermittently, not in total blindness, but in repeated interruptions that fracture perception at the worst possible time. This kind of vision loss is deceptive. It does not feel dramatic enough to stop movement. Instead, it degrades awareness gradually, creating a false sense of manageability. You can still see, technically, but clarity comes and goes. Depth perception wavers. Peripheral awareness dulls. In terrain threaded with roots, rocks, and uneven ground, that margin is everything. The black widow's ecological role explains why this mechanism exists at all. These spiders prey primarily on insects and other arthropods, subduing them with venom that immobilizes without destroying tissue. Against large animals, the venom is not meant to kill, but to deter through overwhelming discomfort. A predator that experiences hours of cramps and distress after disturbing a web is unlikely to repeat the mistake. The spider does not need to escalate. Time does the work. What makes human encounters particularly risky is that the venom's effects encourage exactly the behaviors that increase secondary danger. Sweating increases fluid loss and discomfort, prompting more movement. Muscle cramps encourage stretching and shifting weight, destabilizing stance. Nausea distracts attention inward, away from footing and surroundings. The body is pulled into constant adjustment, never settling long enough to regain full control. In this state, the eye becomes collateral damage once again, not because the venom targets it, but because the eye is where all these disruptions converge. Sweat runs freely. Hands are busy. Vision is already compromised by tearing and blinking. The environment, unchanged and indifferent, waits for a misstep. This is a recurring theme in nature's most effective defenses. Permanent injury is unnecessary. Temporary impairment at the wrong moment is enough. The venom does not need to blind you for life. It only needs to blur your vision while you are standing on uneven ground, near sharp objects, or navigating obstacles that demand precision. Physiologically, the response to black widow venom highlights how tightly interconnected the human sensory and motor systems are. Pain alters gait. Muscle tension changes posture. Sweating affects grip. Vision, dependent on stable head position and clear ocular surfaces, suffers as a downstream effect. The body tries to compensate, but compensation itself consumes attention and energy, accelerating fatigue. In animals adapted to these environments, similar disruptions are managed differently. Predators encountering black widows often retreat immediately, minimizing exposure and avoiding prolonged systemic effects. Many species recognize the spider's web patterns and avoid them altogether. The forest has integrated the widow's presence into its behavioral fabric. Humans arrive without that context, relying on improvisation under stress. The aftermath of a bite can last hours, sometimes longer, even when medical outcomes are ultimately benign. During that window, the risk is not the venom alone, but what it enables. A fall into water while nauseated and cramping. A slip onto sharp roots while vision is compromised. Cuts that become infected because sweat and debris were smeared into wounds without notice. These are the secondary consequences that rarely make headlines but define real survival outcomes. This chapter aligns directly with a core truth your channel returns to again and again. Nature does not need to finish the job itself. It only needs to destabilize you long enough for gravity, terrain, and your own reactions to take over. The black widow exemplifies this perfectly. Its venom is precise, efficient, and restrained. It does not destroy, it disrupts. As the cramps eventually ease and sweating slows, clarity returns unevenly. Vision steadies. Balance improves. The forest looks the same as it did before the bite, unchanged, neutral, almost serene. The spider is gone, its web rebuilt elsewhere, its strategy validated once more. What lingers is not fear of blindness, but a deeper understanding of timing, of how small predators leverage physiology rather than force, of how the most dangerous moments are often those where impairment feels partial, manageable, and therefore easy to underestimate. The black widow does not need to blind you. It only needs to remind you that in a complex environment, even temporary loss of control can be enough. The forest never feels more alive than when you disturb something that was never meant to be disturbed. A pile of clothes left overnight to dry in the heat. A boot turned on its side near a wall. A log rolled to clear a path. These are mundane actions, almost domestic, performed in environments that appear calm in daylight. But the rainforest does not reset when humans stop looking. It fills every hollow, every fold, every pocket of shade with animals that are active, alert, and intolerant of being cornered. The Brazilian wandering spider thrives in precisely these gaps between attention and assumption. Unlike web builders that anchor themselves to fixed points, this spider is mobile by design. It hunts on foot, roaming the forest floor at night with a confidence that comes from speed, vision, and one of the most potent defensive venoms among spiders. During the day, it does not retreat far. It shelters wherever darkness and cover intersect, under fallen leaves, inside boots, beneath stacked tools, among folded clothes. These are not traps laid for humans. They are simply efficient refuges in a world where exposure equals death. The encounter begins abruptly because the spider does not tolerate pressure. A hand reaches into fabric. A foot slides into a boot. A log is shifted just enough to collapse the pocket of space the spider was using to stay hidden. The response is instantaneous and explosive. The Brazilian wandering spider does not flee first. It strikes. The bite is not subtle. It delivers shock as much as pain, a sharp, penetrating impact followed by an intense burning that radiates outward from the puncture. Adrenaline surges. Muscles tense. Breathing accelerates. The nervous system snaps into high alert before conscious thought has time to assemble a narrative. This is not the slow, creeping discomfort of a delayed venom. This is a sudden, undeniable intrusion that forces attention inward immediately. And that is exactly where the danger compounds. The spider's venom is complex, targeting ion channels and triggering a cascade of neurological effects that vary in intensity depending on dose and individual response. Pain can be severe. Sweating often follows quickly. Heat perception becomes exaggerated. Tremors or shaking may appear as the body struggles to regulate itself under stress. None of this blinds you directly. None of it needs to. It destabilizes instead. Hands move fast. Too fast. They grab, shake, slap, clutch at the bite site in reflexive attempts to understand what just happened. The spider is usually already gone, having completed its only objective: escape through deterrence. The human body, however, is now in chaos. Heart rate is elevated. Sweat pours freely, slicking palms and fingers. Muscles quiver with excess stimulation. Focus narrows to pain and threat. This is where the face-touch reflex becomes unavoidable. Sweat runs into the eyes. Vision blurs slightly from moisture and stress. The urge to wipe is overwhelming, not as a decision, but as an automatic response. Hands that were just inside boots, under logs, or gripping soil rise to the face. Whatever contaminants were present, dirt, leaf litter, bacteria, spider silk residues, are transferred without resistance. The eye receives them instantly. The reaction is immediate. Burning spreads across the ocular surface. Tears flood the eye in an attempt to dilute and flush the irritant. Eyelids clamp shut involuntarily, driven by one of the strongest protective reflexes in the human body. Vision collapses, not because the spider has damaged the eye, but because the eye is doing exactly what it evolved to do when threatened, shutting down. Blinds fast here does not mean permanent injury. It means sudden functional loss of vision at the exact moment when coordination is already compromised. The body is shaking. Heat feels oppressive. Pain competes for attention. And now, clarity disappears. This loss of vision is profoundly dangerous in the environments where wandering spiders are encountered. Forest floors are uneven and cluttered. Roots snake unpredictably across walking paths. Rocks shift under weight. Tools, branches and debris sit half-hidden in leaf litter. With eyes forced shut or flooded with tears, balance deteriorates rapidly. Each step becomes uncertain. A stumble sends weight lurching sideways. Hands reach out blindly, often contacting rough bark, sharp edges, or irritant plants that introduce new injuries into an already overloaded system. The irony is that the spider's strategy is not designed to incapacitate large animals for long. Its venom evolved primarily to subdue insects and small vertebrates, with defensive potency as a secondary benefit. The goal is not to kill a human. The goal is to create immediate space. Pain, shock, and confusion achieve that far more reliably than pursuit or persistence. Ecologically, the Brazilian wandering spider occupies a unique niche. As an active nocturnal hunter, it regulates populations of insects and small animals that many other predators cannot reach. Its mobility allows it to exploit transient food sources and disturbed habitats. This adaptability brings it into frequent proximity with humans, especially in agricultural zones, rural dwellings, and forest edges where human structures mimic natural shelters. The spider's defensive behavior reflects this lifestyle. When cornered, it does not rely on camouflage alone. It raises its front legs, exposes warning coloration, and strikes decisively if pressure continues. This escalation is efficient and risky, but it works because most predators and humans back away instantly after a single encounter. The physiological response in humans reveals how finely tuned our systems are for environments very different from the rainforest. Pain triggers panic. Panic accelerates movement. Movement spreads contamination. The eye, as always, becomes the weakest link, not because it is targeted, but because it is essential and exposed. Sweating worsens everything. Heat dissipation is critical under stress, but sweat also acts as a solvent and transport medium. It dissolves salts and organic compounds, spreads irritants across skin, and encourages repeated wiping as discomfort builds. In hot environments, this cycle intensifies rapidly. The more stressed you become, the more sweat you produce, the more often you touch your face, and the greater the chance of ocular contamination. The Brazilian wandering spider does not need to pursue or escalate further. Once the chain is set in motion, the environment does the rest. Temporary blindness near uneven ground, tools, or water edges is enough to cause serious secondary injuries. Falls, cuts, and collisions occur not because the spider is aggressive, but because the human body is operating under sudden overload. Animals that coexist with wandering spiders behave differently. Many learn to avoid enclosed spaces during the day or probe cautiously before inserting limbs. Predators that encounter the spider's warning posture retreat without contact. The forest has adapted to the spider's presence through behavior, not immunity. Humans, arriving without that context, rely on reflex. And reflex is precisely what the spider's defense exploits. As the minutes pass, the intensity of the reaction may begin to ebb. Shaking slows. Pain stabilizes. Vision returns in fragments as tears recede and eyelids relax. The environment looks unchanged, indifferent to the episode that just unfolded. The spider is long gone, already resumed its role as a roaming predator in a system that will never notice the disturbance. What remains is not fear of blindness, but a recalibration of awareness. Boots are shaken out. Clothes are lifted carefully. Hands hesitate before reaching into dark spaces. Sweat is tolerated rather than wiped immediately. These behavioral changes are the true outcome of the encounter. This chapter reinforces a central truth that runs through every mechanism in this series. Nature does not need to destroy you outright. It only needs to destabilize you briefly, at the wrong moment, in the wrong place. The Brazilian wandering spider does not blind you with venom. It shocks you, startles you, and lets your own reflexes carry the danger the rest of the way. The frog is almost invisible until it moves, and even then what catches the eye is not shape, but absence. A sliver of green so translucent it seems carved out of the night air, perched on the underside of a leaf above a stream. Light passes through its skin, revealing a faint suggestion of bone and organ, as if the animal were an unfinished thought rather than a body. The glass frog is harmless in every way that matters to human survival. It has no venom, no bite, no toxins to deliver. And yet, it sits at the center of one of the rainforest's most reliable traps. Because the danger here is not the frog. It is everything you do to get closer. Glass frogs live in places that punish curiosity. They choose leaves slick with moisture, suspended over moving water, often several meters above uneven ground. Their world is a lattice of wet surfaces, broad leaves coated in algae, thin branches polished smooth by constant humidity, vines that flex under weight rather than support it. This is not accidental. These frogs evolved to exploit the microclimate of the canopy understory, where airflow is minimal, evaporation is slow, and predators struggle to move without exposing themselves. The same features that protect the frog destabilize anything larger that tries to follow. The encounter begins with misdirection. The frog is small, delicate, almost ornamental. It triggers a very human response. Approach rather than retreat. People lean in, step closer, adjust footing to get a better angle. Hands reach out to steady against a trunk or branch. Leaves are pushed aside gently, then less gently, as balance shifts. The forest responds immediately, not with attack, but with physics. Leaves collapse under pressure, releasing trapped water, spores, and debris. Sap smears across fingers and forearms, sticky and often chemically active, designed by plants to deter insects and seal wounds. Leaf litter breaks apart, sending fragments of decaying plant matter into the air. Fine grit from bark and soil coats the skin. None of this feels dangerous in the moment. It feels like texture, like humidity, like background noise. The frog jumps. It does not flee far, just enough to remain visible, just enough to encourage pursuit. Another step forward. Another lean. Another branch brushed aside. The body is now committed to a posture it cannot easily recover from. Weight shifted, feet planted on uncertain ground, attention locked upward rather than downward. Sweat runs freely, driven by heat and effort, streaking down the face and into the eyes. This is the real trap. The forest's irritants do not need to be toxic to be effective. Tiny fragments of leaf tissue, Fungal spores, microscopic hairs from plants, and sticky sap all find their way onto the hands. When sweat stings the eyes, the reflex is immediate and automatic. The hand comes up to wipe. Contact is instantaneous. Debris transfers effortlessly into the eye. Sap smears across the eyelid and lashes. Fine grit lodges beneath the lid. The response is violent and immediate. Burning flares as plant chemicals interact with sensitive ocular tissue. Tears flood the eye in seconds, an emergency response aimed at flushing out what should never have been there. Eyelids clamp shut involuntarily, muscles contracting hard enough to blur the world into nothing but sensation. Blinds fast here is brutally honest. Vision collapses not because something attacked the eye, but because the eye is doing exactly what it evolved to do when overwhelmed, shutting down to protect itself. One moment the frog is in focus. The next, everything dissolves into white blur and motion without edges. The timing could not be worse. The body is already off balance, leaning forward or sideways, weight committed to a step that has not yet landed. With vision gone, depth perception disappears. The ground, already treacherous, becomes unreadable. A foot slips on a wet root. A branch gives way. Gravity takes over. This is where the glass frog disappears entirely from the story. The consequences now belong to the environment. A stumble sends hands out instinctively, palms scraping against bark or plunging into leaf litter thick with decomposing material. Cuts open along knuckles or wrists, shallow but immediate. Sap seals into the wounds, trapping debris. Water splashes up from below, soaking clothing and skin. The forest floor receives the body without ceremony, indifferent to the reason it fell. From a biological standpoint, the glass frog has done nothing remarkable. It has simply occupied its niche with exquisite efficiency. Its translucent skin is an adaptation for camouflage, breaking up its outline against moonlit leaves. Its choice of breeding sites, leaves overhanging water, protects eggs from terrestrial predators and keeps them moist without submerging them. Males call softly, conserving energy while remaining difficult to locate. Everything about the frog's life minimizes risk through positioning, not aggression. Humans, by contrast, are drawn into risk by movement. The act of chasing, leaning and reaching violates the unspoken rules of the understory. Vision is prioritized upward at the expense of footing. Hands are used for balance without regard for what they touch. Sweat accelerates everything, turning harmless contact into efficient transfer of irritants. The plants themselves are active participants. Many rainforest species produce saps and exudates rich in secondary compounds, phenols, alkaloids, latexes, that discourage herbivory and seal damaged tissue. These substances are not aimed at human eyes, but they do not need to be. In an environment where contact is frequent and wiping is reflexive, they become accidental weapons. Even the leaf litter contributes. Decomposition releases fungal spores and microscopic fragments that irritate mucous membranes. In dry air, these might disperse harmlessly. In humidity, they cling. The eye, wet and exposed, becomes a perfect receptor. Animals adapted to this environment move differently. Arboreal mammals test branches before committing weight. Frogs leap rather than lean. Insects cling with specialized pads and claws. Everything respects the instability of surfaces. Humans, accustomed to rigid ground and predictable textures, override caution with curiosity. The glass frog's harmlessness is precisely what makes this chapter important. There is no villain here, no venom to blame, no bite to dramatize. The danger emerges from interaction with a system that assumes competence. The frog does not defend itself. The forest does. As vision slowly returns, first as light without shape, then as blurred outlines, the consequences of the fall become apparent. Mud coats clothing. Hands sting where skin broke. The frog is gone, absorbed back into the lattice of leaves and shadows. The scene resets, as if nothing unusual occurred. But the lesson lingers. This chapter closes the loop that began with venomous animals and ends with one that could not harm you if it tried. It reinforces a core truth about the Amazon and similar environments. Danger does not always wear fangs or spines. Sometimes it waits in the space between your intention and your balance. The rainforest does not need teeth to take your sight. It does not need venom or claws. It needs moisture, plants doing what plants evolved to do, and a single human reflex performed at the wrong moment. Touch your face once with the wrong hand while standing in the wrong place, and the forest will take over from there.